Welcome to the UCL Lunch Hour Lectures. I'm Paola Lettieri. I'm a professor of chemical engineering at UCL, and I am hosting today's lecture in my role as academic director for UCL East. So today's lecture is the first of a series that we are giving to you at UCL to present some of the exciting activities that UCL East will encompass. UCL East is our new campus at the Queen Elizabeth Olympic Park, where 8 faculties across UCL will bring activities to tackle some of the most fundamental challenges that humanity faces today and will face into the future. So today's lecture, given by Professor Kate Jones and Professor Duncan Wilson, really wants to do that. Some of the challenges that UCL East wants to tackle are about planetary sustainability, and it is really within that context that today's lecture is framed. Internet of Wild Things, you will tell us what that is, using new technological approaches to understand and safeguard our planet. Professor Kate Jones is Professor of Ecology and Biodiversity at UCL, and she's the Director of the Biodiversity Modeling Research Group. She's a world-leading figure in the area of biodiversity. She was awarded in 2008 the Philip Leverhulme Award for her outstanding contribution to zoology. But Kate is also very well known in her area of work for bringing together an innovative approach linking biodiversity, global change, as well as ecosystems services. She has a particular love for the bats, which I expect will feature in the lecture today. And so between 2010 and 2015, she was the chair of the Bats Conservation Trust. So Kate will be delivering the lecture together with Duncan Wilson. He is our new professor at UCL of Connected Environments in the Bartlett Center for Advanced Spatial Analysis at UCL. Duncan joined us in 2018 following 20 years of experience in R&D and in particular working with digital technologies with Intel and Arup. He is particularly interested in working at the interface between industry and academia, and in particular in the area of digital technologies and the Internet of Things, so understanding how these technologies can augment our understanding of the built environment and the natural environment and how they adapt and cope with change. It's all to you now.
Thank you. So thank you very much for that introduction. I can't believe she remembered all of that. That was amazing. So wild nature and natural ecosystems are declining at a rapid rate as we've never seen before, because humans are using more of resources and changing climates. But fortunately, there's been a massive revolution and rapid progress on sensing, so sensing technology to try to understand natural systems and producing vast streams of data for scientists to try to understand how to manage and how to process and then manage our environments better. So this talk is going to be about a review of some of those new technologies, really exciting new technologies, and using some examples from the work that we've been doing at UCL. But I think really importantly, this is a story about how two disciplines have come together to think and create new ideas that have informed our setup of the Institute of Future Living at UCL East. So it's about how I had, there's some big nature problems, big biodiversity problems, big planetary problems that I've stepped out of my comfort zone, talked to Duncan, and then thought about how we can innovate in this space and how can we manage our planet in a more sustainable and a more connected way. So hopefully we'll give you some examples from our work and some ideas about what we're going to do in the new institute and our respective centres. And hopefully you'll be as enthusiastic as we are about this opportunity, about the new campus. Okay, so just to start with some horrifying statistics. So this isn't a depressing talk. but definitely it's a depressing start. So if we can have the lights down just slightly, or do I have to do that? I don't know. Oh, hello. Can you turn the lights down a little bit? Nobody's paying any attention. Like, there's a whole series of things on here that I don't understand. I'm not even like, I don't even want to touch it. Oh, hello. Brilliant. That was magic. Thank you. Here's a technologist. So, okay, so this slide is my attempt at kind of bringing some of the stark realities of the biodiversity crisis. So one of the major reports from the IPBES has been published this week, showing how serious the crisis is of biodiversity on this planet. And we'll think about 1 million species are at risk of extinction. Now, these are all endangered species, critically endangered species, which Joel Sartori, who's got a photo arc project, and he has been trying to photograph and categorize all the endangered species. So I'd recommend you go and have a look at his website, because it's really stunning. So what's this kind of scale of the biodiversity loss? So this is from the WWF Living Planet report this year. So you can see that the red proportions of the pies are species which are endangered. So different animals and plants have different kind of threat levels, but overall it's about a third, quarter to a third, and sometimes nearly 40% of species which are threatened with extinction in the next 50 years. So it is a pretty serious issue. And what is it? Why is this happening? Well, some of the biggest drivers that we think of species is habitat loss. So if you remove forests, wetlands, for example, they haven't got anywhere to live. So it's a pretty obvious result. But there's also things like pollution, exploitation, which is direct hunting or fishing, climate change, and invasive species. So these are species which have been moving around the planet and endanger the species which are already there, so they compete with each other. So what's the ultimate driver of these issues? And it's human population growth. So this is an image from the World in Data website, if you want to have a look at that. So the blue line is showing the human population. So human population was bumping along for most of its existence at a pretty low level, under a billion of us. And then around 1960s, 70s, we had this great acceleration where we have now approaching over 7 billion of us, and by 2050, probably 2100, probably about 11 to 12. So this is due to human growth rates. So they peaked around 1980, but then they've been leveling off. So the human population's been kept in check for millennia by high mortality rates of infants. And there's a huge growth spurt, and now the growth rates are coming down because of education of women, of lower, smaller families. So it isn't it's not as depressing as it could be. This is just something that we've got quite a lot of people, and we're going to get quite a lot more people. So these are the ultimate drivers of why we have these biodiversity trends and losses. And this one I've just put up is an amazing infographic, if you want to have a look. It's by Ed Hawkins, and he's just showing the amount of climate change that's been happening over the last few decades or so to see the kind of temperature changes. So it's quite a nice infographic. You want to have a look. So, okay, biodiversity is declining. Does that really matter to you and me? So does it really matter that that's happening? And I think the body of evidence that's coming out and has been coming out for about 20 years or so says yes. So this is a schematic from one of the reports. You can get many of these kind of diagrams from lots of different sources now. But you've got all of land, living things in the green box. And these animals and plants and the environmental variables are all patched up into ecosystems. So these are interacting environments. And they have some kind of ecosystem service. So this is an incredibly human-focused view of the value of nature. But some of those ecosystems are providing services for us, which are producing goods. So for example, it could be pollination and then crops, which then helps our human health and well-being in terms of our economic value, our shared social cultural value, or our health value. So there's lots of work now that's just underpinning these ideas about our dependency on the natural world. And if you have any drivers of change, if you modify that habitat or intensify that landscape, then you've got some complex interconnections which are being affected, which would impact your services and the goods produced. So, okay, biodiversity does matter, and it does matter that we're losing it. So what are we doing about it? So this is an image from a paper from one of my colleagues, Georgina Mace, who's at UCL. So the point of this slide really is just to look at the state of nature. So the biodiversity index down here is declining. And this is despite massive global efforts to stop this happening. So there have been massive international agreements to halt the rate of loss of biodiversity change across the world. And they've had very little difference on the scale of the problem or even trying to change it into the other direction. So the global goals, the sustainability goals, are for 2030, and our extrapolated trends of the current change of the biodiversity index is slowing, but it's still going to be not meeting any of the Sustainable Development Goal targets. So we need to do something different. Like, we've just totally failed on changing this curve. So we need to bend the curve back up. We need to do something radically different from what we've been doing. So these are some model projections of what I think they're a bit optimistic to us, but these are some model projections of what it could look like. So how do we bend that curve back up? And that's really interesting. How do we do that? And I think one of the issues is scaling up. So scaling up our monitoring and enabling the data to actually inform our practices. So how do we know how to manage farmland better and more sustainably? How do we know how to manage cities better? So I think that the kind of scaling up of data is really important. And I've been talking a lot to many different people about this problem, and this really struck me. So it may not be obvious what the link is at the beginning, but this is a view of the industrial revolutions over the last few hundred years. And I think we could really draw some lessons from this. So this is about productivity for industry. And what I'm trying to think about is how could we use that for conservation? So how do we manage the planet with this kind of idea? So you've got Industry 1.0. So these are like the satanic mills of Lancashire or something. You've got steam, power, and energy, and and this mass production in Industry 2.0. So you can think of like a Ford factory putting stuff together and shoving stuff out. And then you've got Industry 3.0, which is computers and automation. So like a Samsung factory or something like that. So you've got robots doing part of the work so that you can increase production. And Industry 4.0, which is some mythical thing, that you've got these cyber-physical systems. So you've got robots which are able to make decisions about the environment and enact some decision-making process to manage the factory and manage the process better. So you can think of an Amazon factory, which is ordering more stuff once you buy it, or moving the stock around the warehouse. So how does this relate then? So I would suggest that conservation and managing our planet at the moment is kind of stuck in 1 and 2. So we're all about mass participation in monitoring programs. So there's lots of citizen science programs across the world that are monitoring our planet. There are some satellite systems which are doing the monitoring, but a lot of it is terrestrial based and using people. So one of the examples from this is the State of Nature report, which got published in 2016. So this was launched by David Attenborough. So this was a huge number of NGOs all over the UK using volunteers to observe nature and to understand what the trends were. So this is thousands and thousands and thousands of people that were tracking butterflies or snails or whatever it was to understand what the trends are. So trying to then put that all together into this kind of policy tool that policymakers can take and say, look, biodiversity is declining in our country, we need to do something about it. So these are really powerful things, but policy instruments, really powerful ones. But this takes a lot of energy and a lot of effort. Is there ways that we can move into 3 and maybe even 4? So having these cyber physical systems to enable us to make decisions much more quickly. So that's the kind of space that we're in UCL, in the Institute of Future Living. And the centre that I'm going to be directing is called the Nature Smart Centre. So not just becoming a smarter way of managing our planet, but a nature smart way. So it's kind of at the interface of understanding the links between our health and our environment, but also trying to understand how to scale up these decision-making processes and move into 3 and maybe even 4 in trying to manage our planet. So I'm just going to go through some examples of where I'd gotten to in some of these using machine learning and new sensors in my own work. And then I'm going to hand over to Duncan to talk about how we kind of segued together in some of his work on the centre that he's leading in connected environments. Okay, so there's a massive wildlife sensor revolution. So there's just been innovation, it's crazy, in images and movement and sound. So in images, you have camera traps which you can put up into the environment, and they'll take these remote photos. And they've been around 100 years or so because people were using them originally for hunting, but they've been taken over by the conservation community to provide really interesting insights and monitoring remote locations, or even not remote locations like my garden in North London. So this is one of my favourite images. So this was a project in Liberia that we were involved with, and they put the whole community there put out a load of camera traps in this nature area, and they found the first pygmy hippo that they'd ever discovered. Now I'm showing you this photo because it's a really powerful image, and it was so powerful that the president of Liberia, she set aside this area as a nature reserve. So they have got a lot of power and influence in these kinds of images and these stories that they tell. The other kind of sensor revolution that we have is in movement. So there are tiny, tiny tags now that you can put on animals to monitor their behavior. So this one is about, this is a really fab TV show that came on a few years ago called The Secret Life of Cats. So they got a whole load of villages in Oxford, and they made Cat Central in the village hall. And they gave all the cats owners some GoPro cameras and put them on the cats and let them loose. And apparently this cat didn't do anything, just stayed in the house all day and ate its food. But actually, it was travelling about 20 kilometres a night, stealing food from across the village. So that wasn't probably so welcome for the owners. But there are a tiny tag. So this one is from my colleague's study of Polistes wasps. So this is an RFID tag, the things that you have on your Oyster card or on your bank card. So we put them onto the back of these wasps so you can monitor their behaviour and activity. So it's amazing, all these new kind of sensors that we can get. Now, one that's really close to my heart and my research interests is sound. So we've had an explosion of how we monitor sound in the terrestrial and the marine environment, and the sensors are becoming much cheaper and much more accessible. And so I've been trying to think about how we use sound in the environment to use that as a monitoring tool. So bats are really cool. Let's get that out of the way. But they also do something that's really useful, and they use sound to navigate and to locate objects. So, and identify objects. So they use it, they mostly use high frequency sounds, and it's called echolocation. They bounce these sounds off objects. So in fact, they leak information about themselves into the environment. And because they do this all the time when they're flying around and finding food, it's quite functional. So it's not like a bird call that only calls at a certain time of day. They do this when they're active at night all the time when they're flying. So it's a kind of beacon to say what the bat is doing, where it is, and what it's feeding on. So I've been trying to develop some really large-scale projects to utilize the sounds that bats make to monitor populations, to provide this information that we need in order to manage our environment better. So this was a project I set up in 2016. We started off in 2006, actually, gosh. We started off in Transylvania, because where else would you start a bat monitoring program off? And then we've replicated it across different countries in the world, using local volunteers and empowering them to do their own surveys to report back to their national governments. So some of them are more successful than others. This is me in a truck in Mongolia floating down the river with my boss's car, so that was good. So, okay, I've been moaning that we don't have enough data. Now that with all these sensors, we've got so much data, and I've got petabytes of data from these recordings. So I've got thousands of people, thousands of recording. It's taking up a lot of space on the UCL server. So how do you go through it? You know, how do you kind of automate these things? I've got too much to go through manually. How do you do that? And that's where this innovation has come from, in terms of developing new algorithms and new technology to go through and recognize the bat species present and what else is in these recordings. So there are lots of ways to do this, and I'm putting up something which you can have a look at online later, called iSpot. And in iSpot, they took a different approach. So they've used a whole series of people, of crowdsourcing, to identify images. So you upload the image onto their website, and there's a whole series of experts behind there that will log on and tell you what it is. So, you know, they sit there. It's amazing how the return rate is for getting an identification. It's like a minute or something. So it is a little bit crazy. So you have a whole network of experts. So that's fine to get the humans to do it, but whether we could take the humans out of the loop and develop algorithms to do that instead. So I started to think about how to do the bat analysis, and I got in touch with the Zooniverse crowd. So these are astrophysicists at Oxford, and they set up this crowdsourcing site because they had the same problem, well, much bigger problem, that they had the Hubble Space Telescope data, and they had to go through it and analyze it. So what they did was set up a crowdsourced site where you have the images and you ask the public to go through and classify galaxy shapes. So I got in touch with them, and they've got a whole series of other projects, one on climate change and lots of other things now, to see whether they could help me do something with the bats. So we set up, of course, a website called Bat Detective. So you are on the search for bats, and you get presented with some of the data from the surveys, the IBAT surveys we've been doing. And I asked the public to help me classify what a bat was. So you could play this, and you've got insect calls as well, other things in there. You've got different types of bat calls, because they sing to each other as well, and social calls. And they have a feeding buzz when they get closer to insects. So there's lots and lots of things that bats do, and you can pick these out in the recordings. So I got about 500,000 labels in order to train new algorithms to help me understand how to go through these data. And I had 3 users who did about 50,000, 75,000 each. So I don't know quite why they did that. I'm very grateful. Thank you very much. But no, that was absolutely brilliant. And so this was featured in British Science Week a few years ago, and it really boosted how many people took part. So on the basis of this, we developed these new algorithms to go through the calls. So you have the original call, which is at the top in A, and then you transform it into, you kind of reduce the data dimensionality a bit into this spectrogram so you can kind of see it a bit more clearly. And then you can develop algorithms which find the call in the recording and then take some features from it. So how long it is, how loud it is, what's the top frequency, what's the lowest frequency. So you can take out a load of features and then you compare it to a library that you've already collected to understand what species you have. So I got together with a lot of computer scientists from UCL and elsewhere, and instead of doing it that way, which has got its limitations because you don't know whether you've collected the right characteristic or not, we use something called deep learning, which is the latest thing in machine learning. So it doesn't need the features because it learns them as you go. So it means that you can find the call and identify it all in one go. So we use these deep learning technologies to develop new algorithms to find calls. So the red parts are where we trained the algorithm, and the black parts are where we tested it. And we also tested it on a totally different system in the UK, and also in a project in Norfolk using different detectors. So we think that sensors. So we think that this is robust to lots of different species and lots of different applications. And these curves just show you how good ours is in comparison to existing technologies. So ours are always in the far right. So the very far right is where we've got really, really high precision and accuracy. So if I just show you, so the red parts there are where we're identifying calls. That was a bat call, by the way. So slowed down. Okay, so not just identifying where detecting where the call is in the sequence, but actually classifying it to species. So we've been developing that side of that as well, so that you can now actually detect and identify the species in microseconds in petabytes of data, which is incredible, and the first time that's ever been done. So this is working with a lot of computer scientists and ecologists in my group. Okay, so just to kind of wrap up this section, that's fine that we've got these algorithms, but I was talking about conservation 3.0, and we need to go from data to decisions. So this is an example from the guys in Jersey, which took part in the IBAT's Jersey program. Just in case you've temporarily forgotten where Jersey is, it's off the coast of France. It's tiny. It's very big, but it's easily done in this approach, and it's more because you can get a lot of coverage. It's more like a census than a survey, to be honest. But they covered the island for many years using our acoustic approach, and I think I'm just using this as an example to say you can get the volunteers to help generate the data, and then these are the population trends from going from data to the trends, and you can then report that to the government about how they've been working. So the opportunities then are quite big with these new technologies. So we've been developing new types of sensors, which are much cheaper, like this big, and we're developing a new national survey for bats, which everyone can take part in. You would choose the square that you want to survey, and then upload your data using our algorithms, and then get your report back immediately. So you can put it in your garden and find out what bats you have. And so this landscape approach is not just for the UK, but we also have, we're working with WWF, looking at the health of ecosystems in general. So we're working across 4 biomes across the planet, and we've been using a variety of different technologies to understand across a gradient what the tipping points are for different species. So we're using camera traps and audio sensors to characterize in pristine, degraded landscape and where those species fall out of that, where the tipping points are for those species. And so we can then start to understand how to put them back in, rewild these areas. So, okay, so these are all 3.0. There are no kind of cyber embedded systems. And that kind of the closest, I guess, we've got at the moment is these apps that you can get for your phone, which do some of the AI on your phone already. So these are really interesting. You should download some of these. So this is Cicada Hunt, which hunts for a certain type of insect. Chirpomatic, which is a brilliant name, identifies birds by their calls, so you can hold it up and get some interesting IDs. There's a bat one even, working with some colleagues, and this one is new, called Seek, which it tells you what species are in front of you. So these are really, really interesting area where we're trying to explore this computers and automation, but yet we're still not at 4. So that's where Duncan comes in.
And I think there's been a really interesting parallel that's been happening within.
Is your microphone on?
Within my area, within the built environments, and so in exactly the same way, we're trying to understand how we can use digital technologies to instrument, observe, and augment our understanding of how the built environment works. It's been really interesting kind of working with Kate over the past few years and sort of seeing some of those parallels start to emerge. So, for example, we have fantastic models of how we think the built environment works. This is an agent-based model shown on screen here by a colleague in CASA. And this was an agent-based model that was trying to understand how people flow around a space. Now, this was trained on data from Hyde Park, actually, and doing observations in Hyde Park on how people move around it. And that model was then applied into the Olympic Park to help try and understand how people might navigate or move around that space. But the thing that's missing for me within these, so this is kind of great Industry 3.0 examples, I think, but the bit that's missing for me is this feedback loop that helps us to understand whether the models that we're creating of the world are actually true to life, or how they might change over time. So one of the things that we've been doing is looking at the kind of technologies that we can use, as Kate mentioned, to do some of this instrumentation. My first real example of this was on the Millennium Bridge in the early 2000s. I don't know how many people know the story about the wobbly bridge in London, but I used to work for Arup. The bridge opened, on the day of opening it started to wobble, so the bridge was then closed. And what was interesting here was that there was this unusual observation of something. The designers didn't know what had gone wrong, if you like, with this. They hadn't anticipated this might happen. They then came up with a theory as to why the bridge was wobbling, which they then had to then go and test to build up evidence around why that wobbling was occurring, so that they could then go and take mitigating actions to then stop that event occurring. So we got a call to basically say, got a call to R&D saying, we need to capture the footfall on the bridge, because the reason why it was wobbling was this thing called synchronous lateral excitation, which basically means that when people walk, they put their foot on the floor, there's a force going down, there's also a small force going either side, or it goes inwards if they're a bit pigeon-toed. And this effect is basically the accumulation of all of those forces, making the people actually sway the bridge. And it was just something that they just hadn't necessarily observed before. Anyway, so we used a system, captured data for 2,000 people walking across the bridge, related that to the accelerations on the bridge, understood what the phenomena was, then we put in dampers onto the bridge to stop that effect occurring. At the time, I didn't know that was an Internet of Things project, but it was. There was 56 wireless nodes all communicating data in real time. The sad thing was that we went from 3.0 to Industry 4.0. We had this bridge that was telling us how it felt in real time. So once the thing had been proven, we then removed all of that technology, and the bridge went back to being a dumb bridge. And so since 2002, we don't have any data on how the bridge has been feeling over that time. And I would argue that's kind of, would that be a useful thing to be able to capture? But buildings actually often are heavily instrumented. So there'll be hundreds of sensors in this room. And I think what's kind of interesting is how we can start to think of these buildings as robots that just don't move. There's lots of things that are being controlled, from heating, ventilation, air conditioning, through to lighting systems, through to the energy use of the building. But typically all these systems are kind of, if you like, closed loop. They're all on separate networks. They're all installed by different people. And so they're separate entities within a building. And I guess since the 80s, we've had this notion of intelligent buildings. And we've been getting buildings to work quite hard for us and to do things for us. But But again, it feels to me as though it's still at that industry 3.0 phase. We're just automating some of the processes. I think what becomes interesting is when you start to then get that feedback loop, so the building can start to learn over time. Now, I was drawn, if you like reading sci-fi, I read this book in the late 90s by Philip Kerr called Gridiron, which is maybe what got me into this area in the first place. The basic premise of this book is that it's about a software engineer who's developing all of these systems for the building. And in his lunch hour, he plays games like Doom and Quake, as a gamer does, and goes back to work. But what the premise of the book is that the building doesn't understand between the software engineer programming the building and the software engineer having his lunch break. And so the building basically learns, I'm going to spoil the book here a little bit, the building learns how to kill people. So the premise of the book is that the building opens and it starts killing people. So there's some interesting links there through to kind of the Bayesian algorithms that we're starting to talk about as well. But again, how do we start to get to this situation where buildings are starting to learn? Now, we have lots of the building blocks for this. So, for example, in 2014, we did a lot of monitoring of air quality within the borough of Enfield. So this is a visualization from again a colleague in CASA of NO2 levels across London. The one to the left is actually Enfield, which is one of the 33 boroughs. We've got a fantastic array of 100 air quality monitoring stations that King's College manage for London that report up to Brussels to make sure, and the other things that people will find is if we're exceeding limits of pollution. But there's 100 stations across the whole of the city, which means there's 3 in Enfield. We've also got these fantastic models of what that then means for pollution distribution across the area. So the image that you see there is actually a model of what we think pollution is like. It's not actually a representation of pollution. It's not measurements at each of those pixelated points. So our premise was, okay, well, could you start to actually put up a grid of 100 lower cost sensors in there and to try and validate if that model is as accurate as we think it is. But it's also to then try and get this feedback loop going. So in all the measuring of air quality that we did, unfortunately, we didn't improve the air quality at all, because measuring air quality doesn't equal improving air quality. So again, as Kate was mentioning, in terms of trying to move that curve, we suddenly kind of hit this kind of, okay, well, actually, now how do we start to do that? So we had a sense of things like, we suspected that congestion was being caused at the school during the school run, because we would observe that actually there was less traffic during the holidays, school holidays, and traffic, as you can see from these maps, is a big influencer of pollution. But also things like the council are interested in, when we put in speed bumps in side roads to try and encourage cars to stick on the main routes, does that reduce air pollution? Or actually, does the speeding up and slowing down of cars increase particulate matter in the side roads? And we don't know. These are all questions, actually, we don't really know the answer to these yet. People have hypotheses, but we haven't got the data to back it up. Okay, so what are we doing in the park? So we're taking these technologies, and from a connected environments perspective, we've got 3 different areas that we're focusing on. There's extrasensory, AI at the edge, and continuous post-occupancy information. So from an extrasensory perspective, what we're meaning here is that we're interested in both the ways that we capture information and where it comes from. So the top image is there by colleague Sharon, who's in the audience. Looking at the social stream, so looking at social media data, so kind of non-usual sensor data that you might think of, but from that understanding kind of patterns of behaviour in the park. So there's 2 highlighted blocks there. There was semantic analysis done of the tweets and Facebook posts over a period of time. And it turns out that Westfield seemed to be a bit more anxious, and the green space in the park where the playgrounds are seemed to be more positive. Now, there's a massive context behind these, yeah? But these kind of hints as to what kind of new signals could we start to extract. And the second side is then also how we communicate the information. So we've got fantastic VR tools and AR tools, and I've been using them again since the 90s. We've had them, they're not a new phenomenon. They're getting better and better and more accessible, but we've had them for quite a long time. Yet I still have not been to a single design meeting, for example, in UCL, where we're having a discussion about the project and we're sitting in VR headsets or augmented reality and using these tools to make decisions. We still use PDFs and Excel spreadsheets. So what steps do we need to take to start to use these kind of models where we can show all this information that we're capturing in these 3D environments? When does that become the sorts of tools and environments that we start to do this discussion and decision making within? That's another area of research. And the AI at the edge. So as Kate alluded to, we started working back in 2016, 17. And the basic premise there was, we can do this fantastic analysis on this desktop machine here in the office, and that's fantastic. But actually, can we do it in the park in real time so that we're just getting the classifications out? And so this box here, in effect, is that. It's the first version of that. The goal was to be battery powered initially. It's really tough to do that. But we've got 15 of these devices out in the park that have been running for multiple years. But in addition to the actual all the technical challenges that were solved to try and compress all those algorithms down into a small computer and still do the analysis, that's all challenging, and that's fine. But there's a whole other side, which I think is at least half of the effort expended on these research projects, which is just keeping the thing on for 2 years. And don't underestimate the amount of time and effort it takes to do that and the challenges that people face. Yeah, it's harder to get that written into kind of grants sometimes. And the hard thing that often people within the domain of Internet of Things talk about is they say that the hardware is the hard bit. The things are typically the things that tend to fail. So again, a huge effort has been put in trying to figure out how to make these things more sustainable, reliable, and get this continuous monitoring. And that then loops back fully through to the continuous post-occupancy information. We've got a fantastic opportunity within the UCL East and the East Bank development in the sense that people are very aware now of these kind of visions of smart buildings and smart districts and smart areas. And so it's really good support from the top level to try and make these things happen. And we've got lots of the building blocks to try and enable these smart environments. And so this idea of trying to understand how things perform according to their design intent, I think is really interesting. But what's super exciting about working with Kate and her team within Nature Smart is that it's not just the buildings, it's the environment around the buildings. And the biodiversity is also affecting cities. It's not just out on the savannah, it's not just in Nepal, it's also where we are here as well. And so I think the opportunity that we have from a UCL perspective to do really interesting research in the park is very exciting.
So I just wanted to just finish with some results from our survey from our sensors. So this is kind of illustrating that in our models, we think that the events in the stadium are having a big impact on the bat activity in the park. And this is just a kind of infographic from a real-time recording from from our sensors in the park, so you can have a look at those online. But the point is that the lighting and the activities in the park are having a clear impact on the biodiversity in the park, but we're still not quite closed the loop. So exactly what do we do to optimize, say, people's safety for turning down the lights, for example, and having more biodiversity on the park? So how do you balance the needs of people and the needs of biodiversity in these areas, and how do you optimize that? So we still don't know that, but we're getting closer to 4.0. So I just want to then stop by just saying, I think there's some really exciting opportunities within the Future Living Institute between the two centres, and there are many other centres in the Future Living Institute. But I think there's a really exciting opportunity to turn the campus into a living laboratory, to ask these questions, to give it as a flagship project for around the world, and for our researchers, our students, and for community engagement with the public and our partners in the rest of the park. So I just want to say thank you from Duncan and I for the invitation to give a talk.
Shall I ask a question then? Yeah. You've mentioned about the targets, 2030, and then we also know that we're signing up to even more challenging targets to be carbon-free by 2050. Do you think that these targets are achievable, or to just pave the way to basically make them achievable in your area of work? How do you think we should be using the Internet of Things to do that?
So I guess, from my perspective, I think that we've been If I take the example of energy use in buildings as kind of one of the things that affects our environment, at the moment there's a kind of a folklore, if you like, that any of the energy models of a building, the actual energy use of a building is roughly twice what was modelled. And Stanford did a survey of over 5 years over 200 or so buildings, and it came out pretty much as a constant. So that means that we're kind of, I mean, it's good that it's constant, it's good that we're all equally wrong, but surely it would be better to start to try and figure out why and what is making our decisions incorrect. Because that's the way that we then are able to sort of try and take the more positive actions. That's what I mean. Kate mentioned the data-driven decisions. It is as simple as that in some ways. But, it's gathering the data that's needed to be able to change the direction that we're heading in, but making that data understandable and relatable to people. I think that's where potentially we're missing out, and that's kind of the conversation at the moment. It's curious to me how the phrase climate change is being changed to climate catastrophe and to other phrases because it's not having that impact. People saying, oh, it's just a change, it's fine. So I think that's one of the big challenges that we'll have.
Yeah, I think I worry that even with all this data processing and data-driven decisions, it might not be enough because people don't make decisions based on data. And often the politicians have to balance a huge range of things when they're making a decision, and data is just one of them. So I think there has to be some kind of bigger change of our priorities and what kind of planet we want to live on. I think we're at a tipping point of trying to change that, and if we don't do it soon, we'll be down one path. So I think it's also, I'll just add that it's also political, and it's our political will to change. So will we meet the targets? I don't know. I hope so.
On that note, just when you have your teaching at the institute, will the public be allowed to visit? I mean, how do you open up your learning to the rest of it?
It's a really good question. And when we set up the UCL East and our ideals behind that, we wanted to replicate the vision that UCL was set up with, was a dodgy part of town that wanted to be open to women and people that aren't religious. We wanted to replicate that at UCL East. And so our whole design is about openness to the public engagement, and a new way of interacting with our researchers and our teaching and the public. So I think it's embedded in all of our programs how we're going to be open.
Could I ask you to join me in thanking again Professor Jones and Professor Wilson? Thank you.